In this final tutorial, you'll learn about some other dimensionality reduction techniques, including nonlinear methods. But first, let's have a recap of PCA and why it's so useful in so many applications. The big picture of PCA is that it finds a low-dimensional basis that describes most of the variability in your data. We often call the subspace that's generated by this basis the latent subspace. And after the transformation, we often call this the latent representation. Latent means hidden because these components are not directly observed in the data, but they're inferred from the structure. PCA has a number of different applications, and I'll go through four that are very useful. So first of all, PCA, as you saw in the last tutorial, can be used for compression. That's related to the fact that PCA has an alternate formulation as finding the low-dimensional basis that minimizes the reconstruction error. So instead of saving your full data matrix X, you can save the truncated scores matrix and the corresponding coefficients. Second, PCA can be useful for denoising. You saw this also in the last tutorial. So to understand this a little more intuitively, we can imagine a data point that's given here in black, and I'm going to show you in blue a noise-corrupted sample of that same data point. But then when you project onto the low-dimensional subspace, you're basically removing any noise that's orthogonal to that subspace. So PCA can also be used for denoising for this reason. And third, PCA can be very useful for whitening, which is a procedure in which you decorrelate your data and you standardize it, meaning that you rescale it so that the individual components have unit variance. And we saw in the first couple of tutorials that PCA finds transformation so that the new components are uncorrelated, and we know that the variance of each component is given by the eigenvalue. So we can just rescale this so that the new components are uncorrelated and have unit variance. So these first three properties that PCA can be used for compression, denoising, and whitening are extremely useful in a very wide variety of settings. And actually, if you want to do a more complicated nonlinear dimensionality reduction technique, it's often useful to use PCA as a pre-processing step for exactly these reasons. And the fourth application is visualization, maybe one of the most common applications of PCA. So this is another example of a very common machine learning benchmarking data set. This is the iris flower data set. So each sample corresponds to different measurements of a particular type of iris flower. And these are the three examples: virginica, versicolor, and setosa. And you can see that if you just plot the first three principal components, you see some clustering of the data, and you can see that the first principal component describes shows differences between virginica, versicolor, and setosa. This is not something you necessarily expect with PCA because it's not baked into the algorithm, but sometimes you just get lucky and see some kind of clustering when you just look at the first few principal components. Now, what about the MNIST data set? Well, we saw in the previous tutorial that if you look at the weights corresponding to the first principal component, it looks kind of like this superposition of a 0 and a 1. So what does that mean? If we have a sample that's a 0, that 0 is going to lie on the red lobes of the weights. And so when you take the dot product, you'll get a very high value for the score corresponding to the first principal component. On the other hand, if you have a sample that's a 0, that's mostly going to lie on this blue region in the middle. So you'll get a very low value of the first principal component score. So that means that we already expect that there should be some kind of clustering aligned with the first principal component of 1s and 0s. But this doesn't really say anything for what will happen for the digits between 2 and 9. So this first exercise, you will use PCA in order to visualize the full MNIST dataset.